All right, let's talk about something we get mixed up all the time, and I mean all the time. Mass versus weight. We use these words like they're the same thing, but honestly, in the world of science, they are worlds apart. I mean, seriously, think about it. You go to the gym, you jump on the scale, and you say, ugh, I need to lose some weight. But is that what you really mean? Or if you want it to be super accurate, should you be saying, I need to lose mass? It sounds weird, right? But let's get to the bottom of this. And you see this confusion literally everywhere. Take a look at this recipe. It says to weigh out the flour, but then it gives the measurement in grams. Now, grams are a unit of mass, so technically, that's not quite right. But hey, we all know what they mean. And it's not just in the kitchen. It happens even in professional settings. You know, a doctor will tell a proud new parent, your baby weighs 3.5 kilograms. Again, see what they did there? They used the word weighs, but the unit, kilograms, that's all about mass. It's just a habit we've all fallen into. So what gives? Is everybody just wrong? Well, not exactly. But to really get what's going on, we need to pull these two ideas apart and look at them separately. So let's do this. First up, let's tackle mass. For a second, I want you to completely forget about things like gravity or planets. Just think about the actual physical stuff that you're made of. At its core, mass is just a measure of how much matter, how much stuff, is packed into any given object. It doesn't matter if it's you, a planet, or a cup of coffee. Everything has mass. It's the measure of how much of it there is. You know, a classic balance scale like this is the perfect way to visualize it. It's not really measuring weight, it's comparing the amount of material. It's asking a simple question. Does the pile of stuff on this side equal the pile of stuff on the other side? That's all mass cares about. So, here are the absolute key things to remember about mass. 1, we measure it in kilograms. And 2, and this is the big one, it's constant. Your mass never, ever changes. If you have a mass of 70 kilograms here on Earth, you'll have a mass of 70 kilograms on the moon, on Mars, or floating in the middle of deep space. That number is your number. Period. Okay, you got mass? Good. Now let's bring that troublemaker back into the picture. Gravity. Because the second you start talking about gravity, you can finally start talking about weight. And here it is, the single biggest difference. Weight is not how much stuff you're made of. Weight is a force. It is the specific force of gravity pulling down on all that mass you have. No gravity, no weight. Simple as that. It's like a cosmic dance between two partners. You have your mass, which is always there, and then you have a planet, like Earth, which has this massive gravitational field. Weight is what happens when that field grabs onto your mass and pulls. That pull is your weight. And because it's a force, we don't measure weight in kilograms. Nope. The proper unit for weight is the Newton, named after the guy who basically wrote the rulebook on all this stuff, Sir Isaac Newton himself. Okay, that's enough theory. To really feel the difference, we've got to see it in action. So buckle up. We're going to take a little cosmic road trip to put all of this to the test. So let's meet our traveler, an astronaut with a mass of exactly 70 kilograms. Now remember, this number is our anchor. It's our one constant in this whole journey. No matter where we go, her mass is going to stay locked in at 70 kilos. Okay, and here's where things get really fun. Every place has its own unique gravitational pull, which scientists call G. Here on Earth, it's about 10 newtons for every kilogram of mass. But look at Mars. It's way weaker, only 4. And then there's the giant, Jupiter, a crushing 25. And way out in deep space, it's pretty much 0. So how do you figure out our astronaut's weight? Well, the math is actually super simple. It's just weight equals mass times gravity, or W equals M times G. So on Earth, that's her 70 kilograms times Earth's gravity of 10. Boom, her weight is 700 newtons. Now let's watch what happens when she starts traveling. This chart just lays it all out. On Earth, she's 700 newtons. But then she gets to Mars with its wimpy gravity, and her weight just plummets to 280 newtons. That's less than half. But then she goes to Jupiter, and its insane gravity jacks her weight up to a staggering 1,750 newtons. Let's just look at her mission log here. Are you seeing the pattern? Her mass column is boring. It's 70, 70, 70. Rock solid. But look at her weight. It is all over the map. In deep space, she's totally weightless, 0 newtons. Her weight completely depends on where she is. Mass stays put, weight goes for a ride. So, after our little tour of the solar system, what have we learned? What's the big takeaway here? Let's boil it all down one last time. Here it is, the final showdown, plain and simple. Mass is the stuff. It's measured in kilograms, and it is always the same. Weight, on the other hand, is the force of gravity on that stuff. It's measured in newtons, and it totally changes depending on the local gravity. So let's just say it loud and clear for everyone to hear. Mass and weight are absolutely not the same thing. Not even close. And that brings us right back home, to that scale in your bathroom. Think about it. The number it shows you is in kilograms, a unit of mass. But what it's actually doing is measuring the downward force of your weight. So I'll leave you with this little puzzle. What is that machine on your floor really telling you? Thanks for tuning in.